So thank you very much. And today I'm going to talk about the second revolution. There was the revolution of the Industrial Revolution with the invention of the steam engine. Then there was the revolution with the invention of electronics. And now there is the evolution with the invention of big data and where this is going to go. Okay? But remember, I'm a material scientist, and I look for applications. Hold on. Okay, this is a good application. Okay, good, the right direction. Okay? So I'm looking for application because I want to discover new materials. Okay? And I thank the Fritz Haber and the Max Planck Society for funding me for this year of sabbatical. Okay, so now, all right, so I know that some of you actually are like me. They're interested They're interested in understanding new materials, and I will tell you some example how we can use data mining and machine learning to find material properties. This is an example, okay? Vibrations are important, okay, in life, are very important. This is an example of titanium carbon systems, okay? Many of you do not use this phase diagrams, but you know, titanium has a peculiarity that at low temperature we have the alpha titanium, which is an HCP phase. If you use your AIMS or quantum espresso or VASP, you will find that the ground state is titanium. But at really high temperatures, we have the BCC phase, which is called the beta phase. Okay, this is just an example. The transition here is completely vibrational stabilized, and it has effects even if you don't care about titanium. Because if you want to make a super hard material, for instance, this titanium carbide, thick. Okay, and here you have the carbide here, and you were going down in temperature because the carbide can be used for drilling bits or for tips of high temperature tips, right? You see that because of this transition, vibrational transition, there is this line, there is these lines, and then the formation of all these other shapes of carbides. Okay, so you see that even if we don't care about the phase diagrams, the fact that we have a vibrational driven transition actually affects also technology. Okay, how it affects technology? Because when you study ab initio, right, when we do calculations, we always like to minimize we like to minimize the Gibbs free energy, but we can't. So we really minimize the enthalpy. And the enthalpy, these are pieces of phase diagrams, and depending on how are the enthalpy of mixing, we understand what forms. But we do not understand how it forms. Because to understand how it forms, we need to understand that the entropy, in this case the vibrational entropy, which is going to give information about the position of the melting point, the miscibility gap, how big is the miscibility gap, and how big is the solid solution. Okay, so bottom line, we need to understand entropy, and in this case, since this talk is about vibration, we need to understand vibrational entropy. However, understanding vibrational entropy is very, very complicated. Why? Because vibrational entropy requires the understanding of the phonon spectrum. How the vibrations, atoms are like balls, they're connected like springs. The springs are the bonds, in the first approximation, and all these things vibrate, and they create heat, okay? So, well, with heat they vibrate. And then we want to understand how the heat and the vibration interact against each other. So this is vibrational thermodynamics. However, you cannot calculate this for all the materials, and that's why I put these blue things, because it's going to be a surprise. So we need to guess what is the vibrational contribution with respect to some simple descriptors, okay? And we'll figure out which are the descriptors that are more important, okay? Look at here. First of all, we go on the database. This is my database, but we could have gone on the Nomad. And we pick a set of candidates materials. We choose to pick around 300 materials. This is completely agnostic, because if you want to teach a model, you cannot bias the model with your choice. So you really close your eyes and you pick these things like this. Really, the more anoxic, the better. And for these 300 systems, you sacrifice your computer for several months, and you calculate the complete phonon spectrum, which is this X. Okay, this is an example. From that, you calculate the phonon density of states, and since phonons are bosons, you integrate this with the Bose-Einstein distributions, and you get the vibrational and free energies, your specific heat, vibrational entropy and specific heat. This and this are the things that first and the third, that are things that really you interact macroscopically. Well, this is very simple to say, but it takes months and months and months. So you cannot really do this on a high throughput base. However, you can use this 292 to train a model, okay? Well, there are some tricks, but since we lost some time, let's skip these things, not very important, okay? Now, we want to understand the three pictures, the three bottom picture, which is vibrational free energy, and the specific heat. In terms of simple descriptors, this is really the spirit of Nomad. Try to do data analytic out of descriptors, okay? So we choose some physical chemical descriptors and some geometrical descriptors. Okay, so those guys are similar to what Matthias said before, masses, atomic number, positions in the periodic table, number of valence of electrons, really things that are really identity of the atoms, okay? Like the Social Security number if you were in the United States, okay? These guys, the geometric descriptors, are really based, are descriptors that describe the structures, the organizations. You have the Bartok-Partey bispectrum, which is really the fraction of atomic environment. If you're an octahedra, you are tetrahedra, and so on. Or you have the solid angles that you look an atom, and other atoms, you look 3 atoms, and you measure the amount of steradians you have within these triplets. Pair correlation, which is the pair correlation function, which is pretty much the radial distribution function. Okay, so those guys are descriptors that are geometrical structure, and these ones are descriptors that are really identity of atoms. Then you run your machine learning black box. Okay, so in this case we use random forest, but this is not really important what you use. And eventually you're able, with the 300 system that you train, you're able to try to see if you can at least replicate the data and produce predictions. This is an example. This is you always need to check that what you predict fits what the training data. So this is example. Don't remember, but this is prediction is in Y and the calculation is in X. So this is for vibrational free energy, for vibrational entropy, and so on, and for the various omegas, the maximum and the average spectrum omega. Okay, but let's stick with these two. Okay, so this tells us that what the prediction out of the model fits almost exactly the data, the 300 guys that we really calculated correctly. Okay, this works. Let's skip these slides because this just says that the model works for the technological materials. Okay, but now the question is, well, but of all these descriptors, which are the ones that are more important for calculating the free energy? Well, we do a cross-validation, and then in a couple of minutes, 20 seconds, I will remove this black box. And now, in what we try to do, we calculated the RMS error with respect to the prediction and the calculations, and we try to see which one of the various 5 classes of descriptors is able to describe the most. Which are the more important? The structure, the angles, the masses, blah blah blah. So so people like to do phonons, right? So most of the people, actually, if I were doing a poll, they would say the structure, but that's not really true. Look at here. Okay, look at these guys. Okay, the most important parts are specific heat, which is here, and the vibrational free energy. Look, only with the chemical compositions and the properties of atoms, okay, you can guess the vibrational free energy within 12.5 millielectron-volt per atom. If you consider that the configurational entropy is 25 millielectron-volt per atom at room temperature, this is already an error that is already estimates if the vibrations are important or not. We have a simple model based on chemical composition and properties of atoms without doing any phonons, without doing any structure, without even caring about which crystal structure they have. Okay? So then once we have all the data of Nomad, we extract all the data of Nomad and about the fingerprints of the atoms, and we can guess immediately, is this vibrational free energy important or not? Just by looking. And this is exactly an example of accelerated material development, because we are really able to save time in the important materials, and so use the time in the important materials and don't worry about the unimportant ones. Okay, well, let's skip these things. You can do a correlogram, which is try to understand which properties mostly correlate with your information. And you know, if you're colorblind, you will see, look at the cake. If you just otherwise, you look at the colors. And this tells you, for instance, that for instance, the valence is more important than the average size. Okay, so you just kind of get this information and understand which of the atomic properties, you know, the fingerprints of the atoms are more important into the description of the vibrational free energy. Remember that this is because you are training the model to vibrational free energy. If you were training the model for something else, then the descriptor would be different, but you would have some similar results with different descriptors, with different blah, blah, and be able to predict other properties of the materials. There are some methods to predict these descriptors automatically, and you will see in a couple of days the presentation by Luca about the CISO method to find descriptors. Okay? So in summary, what is important are the chemical composition only to get the vibrational free energy. Okay? The second part of my talk is about elasticity and electronics. Okay? Again, this is a work that was published in Nature Communication like a few months ago. This is again training, finding the fingerprints and training a model to predict properties that we do not want to calculate. Okay? Why we don't want to calculate? Because they are too expensive, like before, or because we want to calculate by the millions. Okay, here for electronics and for energies, we chose what we call the universal fingerprints, okay, which are information about the crystal structure, information about the topology of the voids, okay, or the topology of the connectivity. Suppose that this is a unit cell, so the green goes to the green, it needs to go right and left, then up and down. So we code all this information in the same way that people that develop drugs, you know, when they develop the medicines, they try to figure out all the directions they need to go to find the chemical properties they want. And also in terms of nodes and not on connectivity, but in terms of how much the cluster is compact or not. Okay, so those are our descriptors, and we train the model. We train all the energies that we have. All the energies, the band structures, the elasticity, blah, 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 that we have in the database, NOMAD or AFlow, with these descriptors, okay? So look what happens. Okay, well, this is the workflow, but let's keep it okay? Again, we need to test that what we calculate is exactly what we predict. Okay, so this comes out of this is, for instance, the heat thermal expansion. This is what we predict with respect to what we calculate, prediction with respect to calculation, prediction, calculations for various specific heat and so on. But what is important is that now that we want to do accelerated materials development, we don't care anymore about the calculations. Since we know the prediction fits the calculations, and since we are very careful before to do the calculations that were reproduced in the experiments, now the model really goes, we get rid of the calculation, really goes from the predictions to the experiments. This is the purpose of these pictures. So you say the calculated needs to be in agreement with the experiments, the predicted needs to be in agreement with the calculated, you get rid of the calculated, and you go the predicted needs try to replicate the experiments. And this is accelerated materials development for the experimentalist. Because now you don't need to go anymore with the computer, with your quantum code, blah, blah, blah. You can really generate some simple machine learning websites. This is an example. This is online. You can play. This is data analytics websites, right? Okay, and you can really put inside here the position of the atoms, okay, and just press the button, and you have a virtual experiment, where the virtual experiment gives you the band gap, tells you if an insulator, the gain gap, the formation energy, the bulk modulus, the shear modulus, and so on. So you can really play and say, wow, if instead of putting chromium here, I put molybdenum, what is going to happen? I'm going to get a heat capacity that goes down, for instance, or goes up. So this actually is the future. This is probably is the first example of online machine learning applications. Nomad will have a lot of those. For every application, so we're going to give this to Nomad. Nomad is we're going to talk to each other, and Nomad is going to be organized eventually with a lot of applications like this, where the output is the machine learning of a protocol descriptor that has been developed. Okay? Magnets, another things. Then with the magnets that I'm done. The magnets, this is a big challenge because so far the first magnets was discovered like 3,000 years ago. Randomly, they were called magic stones, and the Romans discovered a bunch of magnets. But you know that so far, no magnets have been calculated, predicted with computers. So far, until 1 year ago. Okay, this is an example that this was published in Science Advances, and where we found the first magnets ever. Okay, here, okay, I need to trust me because here the descriptor is kind of tricky, and I do not have a time to explain today. Well, we wanted to look for magnets in the Euler systems. Okay, so Euler, anti-Euler, inverse Euler, and so on. And magnets is a metal. Okay, you know the Euler usually are made with arc melting, so they are made from an environment which is high temperature, which is a lot of disorder. So the proper descriptor for the formability of the Euler compound, and here you need to trust me, was developed before by me and was published in Nature Materials a few years ago. And you know, so if you come from low temperature, low entropy reservoir, you will follow the minimum of H, okay, which is this line. And then in this case, this is a test case, which is boron, samarium, boride, but it's not as important. But if you come from a high entropy environment, like the environment in which you make the Eulers, then you need to follow this green line, follow this equilatent heat locus, okay? And then this is defined by this thermodynamic temperature, okay? And then until you find the proper compound. Bottom line, you see this, instead of trying to discuss about energies, you try to discuss about curvature of formation energies. So this is the key, okay? So when we are equipped with all these temperatures, okay, which are entropic temperature, which are really the curvature, is very simple to calculate, okay, just a little algebra. We go on all the possible Eulers, we calculate them all, it took like 1 year, okay? And this is an example of a ternary phase diagram, so aluminum, manganese, nickel, okay, so you have a lot of those things, and for each point you get the thermodynamic, the entropic temperature. Guess what? Amongst all the systems with the highest possible TS, the highest possible entropic temperature, which is going to tell you what is going to form, you look for the ones that are stable with a very high TS that have not been tried before. Okay, for those you calculate the magnetization. Okay, so if you order them by TS, you find that if the one that are worth trying are a few in the center. Okay, and we predict that this guy is going to form. Is going to be a magnet. We predict that it's going to form. We're going to predict that it's a magnet. Unfortunately, our techniques are not so good that we cannot predict coercitivity. Otherwise, we would have found probably better magnets. But at least we predict that we can find TC. Okay? And guess what? We go to experiments and we find it. Okay? So the example of cobalt, manganese, titanium. This magnet is not going to change the world. I mean, it's not a very strong magnet, unfortunately. But it's very important from an academic point of view because this is the first magnet ever constructed from ab initio, from pieces, knowing what are the descriptors and knowing what are the recipe, in which direction you need to look in the phase diagrams for the magnetization, for the formability, and so on. Okay? And now I'm pretty much I conclude. So, wow, finishing time. So I was fast, right? I conclude, and let me summarize pretty much what I told you today. Okay? The database and the information is very important. It needs to be as good as possible, as broad as possible, as open as possible. But what is important is how we look into, okay? And that's where both Airflow before and this is where Nomad are going to make a difference, because we are making data analytics method inside. This is the key. Okay? Another key is that you need to have a measure of what you are looking for. Okay? And those are called descriptors. Okay? You need to have some sort of parameterization, a simple model that tells you, based on very crude data, that tells you, is this material worth more or less study? Okay? Amongst all the possible descriptors that you can dream, okay, sometimes you are lucky and you guess a descriptor that makes sense. But if you cannot find a descriptor that makes sense, we all would like to find formulas that are scientifically sound. But there are also methods to find formula that do not really require to understand the formula, but they work. Because Matthias has shown before that, the pictures, you remember the two pictures with the colors, with all these lines going left and right? It shows that even if you find descriptors and you accept that you do not understand, the descriptor has information and can be extended to properties that you have not used for training the descriptor. So defining the descriptor is the key. Descriptors plus the data. Okay? And today, I gave you an example of energies. Well, free energies is the beginnings, then energies is the second part, and finally magnetism in the last bit of the talk. Okay, thank you very much, and here for questions. Thank you.